So today we're going to cover complex zeros, which is from 4.3 in our book. One of the things that, or I shouldn't say one of the things, but we're going to practice doing more of our long division in this section that we left off with in 4.2. So you'll get some more practice from this, but please make sure you're doing the homework. It'll give you a lot of practice. I'm kind of showing you how I want the work done. You can't just use your calculator to find all the answers all the time, okay? I won't accept that, but you can use your calculator to start. So the example that I showed at the end of the last video is a really good example of what you will see on the exam and the work I expect. So it'll be very similar to 4.3. 4.3 has us talk about the fundamental theorem of algebra. It says every complex polynomial function of f of x, function f of x of degree n greater than or equal to every complex polynomial function f of x. Let's do it like that. Of degree n greater than or equal to 1 has at least one complex zero, okay? So it says, as a result of the above, we have every complex polynomial of degree n equals 1 or greater than or equal to 1, can be factored into n linear factors, not necessarily distinct, of this form. So this is a big deal. What this is basically saying is every single polynomial that has a degree larger than 1 can be factored into n linear factors. So whatever the degree, if it's degree of 5, it can be factored into 5 linear factors. Now, they're not going to be nice, or they might be nice, but they don't have to be these nice, clean x plus 2, x minus 5. We can start getting into irrational, we can start getting into rational, real, but now we can also do imaginary. So the reason this is kind of a bigger one is because here's the idea. So let's say that we have the real number plane, right? So this is the reals, okay? So that's like 7, 1/3, square root of 5, 17, pi, e, everything's in here. You know, we got 1, -2, square root of 3, 17.28, 1/3, 1/5. You know, we have everything. We have square root of 17, stuff like that, square root of 4. We have everything. Everything's in here, right? This is all the reals. However, it's not really everything, because outside of that, if you think about it like this, there's the complex, okay? So the complex plane has all of those too, but then it also has the square root of -1, okay? And the square root of -1 means that you have all these imaginary numbers. Now, we oftentimes call them complex numbers because they're written in the form. This is the standard form of a plus bi. So a standard complex number would be 3 plus 2i, okay? And you could graph that in the complex plane. You would say this is your real number line, this is I. So we would go over 1, 2, 3, and we would go up 1, 2 i's, and we would put a point, and we'd have our vector right there, okay? So, or basically our version of a vector. So the complex number plane is all the reals. So what we just did in 4.2, it also counts for all of that. But on top of that, now it brings in complex numbers or also imaginary numbers. So normally when they have a real component and a imaginary component, they're called complex, standard form for complex numbers. And then over here, you might just have pure imaginary. Sorry about that. I had to sneeze. Pure imaginary. And pure imaginary are in this form. You know, it's just 3i or 2i or bi. They don't have the real component. Okay. And if you're wondering how can you say that a real number is also a complex number? Well, look, I could just say a real number could be the number 2. But couldn't I also write that as 2 plus 0 i's? So it is in standard form of a complex number, because 0 times I is 0, so it's really just the number 2. So this is how we can write every single real as a complex, but you can't go the other way. You can't write every complex as a real. So thus, the real numbers are smaller than the complex and they fit inside of them, okay? And here's the weird thing, you know, the stuff we'll talk about in calculus. There's an infinite amount of numbers in the reals, and there's an infinite amount of numbers in the complex, but yet the complex number system is bigger than the real number system in terms of cardinality. So that's something we'll discuss a little bit in calc, and we can discuss it in this class if you guys want to talk about it in a meeting or something. So what we're going to do is I'm going to ask you to find all zeros. Okay, so in order to do that, I'm going to give you this first zero right here, negative 5i. But we need this idea right here called the conjugate pairs theorem. And what the conjugate pairs theorem tells us is basically complex numbers or complex solutions do not travel alone. They always travel in pairs. So they say, let f of x be a polynomial function whose coefficients are real numbers. If r equals a plus bi is a zero, so you're saying you have a complex zero, a plus bi is a zero of f. The complex conjugate, r bar, or you could just say the conjugate of that one, that a complex number, is equal to a minus bi, is also a zero of f, okay? So what they're saying is if you know that one complex number is a zero, then you know there is a conjugate that is also a zero. So we're gonna use that to our advantage in this problem, okay? So we know that x equals negative 5i is a zero. We know this, they told us this right here. So then that means by the conjugate pairs theorem that x equals plus 5i is also a zero, okay? So now if I make these both back into factors, so I add 5i, over to here, this would then become x plus 5i equals 0, and this would become x minus 5i equals 0. So what I can do to make my long division a little bit easier is I can multiply these two together and see what they would build. X plus 5i times x minus 5i, that equals x squared minus 25i squared. But you guys should have learned in your previous classes about x squared. Let me just give you a little heads up. So I equals the square root of negative 1, right? So then we can go and say, well, I squared is the square root of negative 1 times the square root of negative 1, which is negative 1. So an imaginary times an imaginary actually becomes a real. Then we can do I cubed. But I cubed is actually I squared times I. But what did I just say that I squared was? It was negative 1. So this becomes negative I, right? Negative 1 times I, which is negative I. But what's I to the fourth? Well, isn't I to the fourth just I squared times I squared? But what's I squared? Negative 1. This is negative 1. That becomes 1. Now here's the weird part. It just keeps going. I to the fifth is equal to I to the fourth times I, but that's just I, so we're right back to here. I to the sixth becomes I to the fourth times I squared, but that's actually 1 times negative 1, but that's actually negative 1. So we're right back to here. You guys see the pattern? It's going to recycle itself every 4. So then I can go, I can go I to the 7th. That's I to the 4th times I cubed, but I know this is 1 times, and we know I cubed is negative I, so this becomes negative I, but that's I cubed. I to the 8th is really I to the 4th times I to the 4th, but that's really 1 times 1, which is 1, which is now back to I to the 4th. So this is cyclic. It has a 4 cycle. It recycles itself every 4. So I could ask you I to the 235th power, and you would divide by 4. Whatever the remainder is, that's the power you're on. Okay, so you'd be on I. So every answer in I, when you're dealing with powers of I, is either I, negative 1, negative I, or 1. There are no other choices for powers of I. So in this case, we have I squared. So then I squared just becomes x squared minus 25 times negative 1, which is x squared minus, plus 25. Now that may sound like a lot of work. This was just me kind of refreshing your memory on I. You've all probably seen it, but maybe not remember too much about it. You feel free again to ask me about that in a meeting. That's what the meetings are for, is you guys show up and ask me for help. So let's look at this. So now we can do long division. So I'm going to do x cubed plus 3x squared plus 25x plus 75, and I'm going to divide it by what I just built, okay? X squared plus 25. Okay, so let's see. Remember I told you guys, what do you want? What does that guy need to become that guy? So he needs an x, right? So then this will become x cubed plus 25x. Now there's a problem. When I draw this, this is an x squared, this is an x to 1. Those are not like terms, so they do not go together. So then I just bring the 3x squared down. He had nothing to do with the 25x. And then this 25x actually goes with that, so they actually cancel, right? So what I should have done is I should have written it over here, minus 25x. That's not my fault. I'm just lining up the fact that this is it skips a power. So now I have 3x squared, that's 0, and I'm going to bring down the 75. I have a feeling the 75 is going to come into play. Okay, so now we ask ourselves the same question, what does this need to become 3x squared? Oh, well, we say plus 3. And then we're going to do the distribution. So this would be 3x squared plus 75. We draw the bar, change the signs, gone, gone, we get 0. Okay, but we knew it was going to be 0 because the conjugate pairs theorem, the complex conjugates, told us, the conjugate pairs theorem told us that the imaginary numbers travel in pairs. So if negative 5i was a 0, so is plus 5i. When I FOILed those out, I got this new polynomial, x squared minus 25, and then I use that for my long division. So that means that f of x can be factored as x squared plus 25 times, x plus 3. Now, if they want it broken down further, you could say, well, this is x minus 5i, x plus 5i, and x plus 3. And that's what the theorem is talking about up here, that every complex polynomial can be broken into linear factors, okay? But the r doesn't have to be some nice clean number. It can be a 5i. So we have this. This would be if I asked you to factor it. So this is in factored form. But what if I just wanted to know the zeros? Well, then you would just say the zeros are x equals 5i. And you could even write it like this, you guys, plus or minus 5i. I'm not sure how the homework makes you do it. They might make you write it like this. I'll do it the way the homework might ask. Homework might say 5i, comma, x equals negative 5i, comma, x equals negative 3 from this guy, right? So they may make you write it as 3 separate ones. I would also take plus or minus 5i. That's totally acceptable. But in the homework, please try to answer the question the way they word it, just to cut down on how long it takes me to get your test back. Okay, so we found our zeros, we found our factors, right? We did everything that we needed to do. And also answer the question how if they say, if they ask you to factor f of x, then these would be the way they want it written. If they want the zeros, then this is the way they want it written. You just have to make sure you answer the question correctly. I will take off points if you don't answer the question presented. Okay, so let's look at another one. Okay, so I'm going to give you guys I'm going to write this one out for you. So h of x equals 2x to the 4th plus 7x cubed plus 4x squared plus 28x minus 16. And you get, they say negative 2i is a 0. Okay, so we're going to do the same thing as last time. We're going to say, well, x plus 2i times x minus 2i, right? Because the same thing we did last time, if we set them both equal to 0, by subtracting x equals 2i, negative 2i, and so on, we'll get it back to this. So then this becomes x squared minus 4i squared, but that's really x squared plus 4 equals 0. So this is my new polynomial that I'm going to use to do long division. So I'm going to come over here and I'm going to do x squared plus 4. Now you might ask yourself, what if they didn't give us one of the zeros? Well, then we turn to our calculator. We try to find one on the calculator and do long division with that one. And then we do the rest with factoring or with our depressed polynomial. But this is the technique I want you guys to try to work with. This is something you need to learn. So then we have 2x to the 4th plus 7x cubed plus 4x squared plus 28x minus 16. I have a feeling this one might be a little bit harder. Let's see. So I need an x squared up here, right? And this would become, or I say, what does this guy need to become this guy? We need a 2x squared. So this would become 2x to the 4th. And now I'm going to try to write this in the correct spot this time, plus 8x squared, right? Because I'm going to put the x squareds with the x squareds. And then I'm going to change the signs. So now this is gone, and I get 7x cubed minus 4x squared, okay? And then I'll put the 28x there. I have a feeling it's going to need to be brought down just like before. Now we ask ourselves a question. We need a 7x, right? We distribute, and we get 7x cubed plus 28x. That's over here. Draw the bar, change the sign. Gone, gone. And this becomes negative 4x squared minus 16. Do the same thing again. What does this guy need that this guy has? So this will be negative 4. So then this would become negative 4x squared minus 16. Draw the bar, change the signs. We get 0, okay? We get our remainder of 0, all right? But again, we knew that was going to happen, okay? So now we know that f of x can be written as x squared plus 4. Now we need the other ones. So here is 2x squared plus 7x minus 4, but we don't know if that's factorable or not. So we can't stop here. We got to keep going. So we're going to say 2x squared plus 7x minus 4. Is that factorable? Well, let's see. Parentheses, parentheses. Minus 4 plus 1. Let's see. That's x. That's negative x. Oops, we got to change the signs. Let's put this plus, and let's make this minus. So the guess and check method is my favorite method to factor. I just keep guessing until I get it, and if I can't guess it right away, I just jump to the quadratic. I would just solve this one using the quadratic, okay? If I could not guess right away. So this is negative x plus 8x. If I do this one and this one and this one and this one, that gives me 7x, and that's my middle term. So this is going to be the factors of it. I'm pretty sure I'm right here. So what we're going to do is we're going to say then that x equals 1/2, right? I solved this one for 0, and then x equals negative 4. So I found this 0, I found this 0. So let me say my zeros are x equals 1/2, negative 4, and then what? Plus or minus 2i. And this would be my zeros. And if they want me to factor it, I have these two factors, and then I have this, right? So that would be my factors. Remember, it's a 4th power polynomial, so it has at most 4 zeros. We found all 4. 2 of them were complex, 2 of them were real. We're feeling pretty good, okay? So this is how you can do these problems on the exam. This is what I expect to see, okay? So let's do one more. So here it says, find all the zeros. It doesn't say complex, it doesn't say real. So if you want to find all, then they mean all the complex zeros. So what we're going to do is we're going to say f of x equals, this is the problem they gave us, x to the 4th plus 10x cubed plus 14x squared plus 250x minus 275, okay? So the first thing I'm going to do is I'm going to graph this on my calculator because they did not give me a 0 this time. So in the previous 2 problems, they gave me a 0, and then based on that 0, I could do long division, okay? And I'm also going to practice synthetic division with you guys on this one. So let's take out our calculators. I'm going to do it on my other calculator so it doesn't take as long. You guys should all take out your calculators and plot this in your calculator. X to the 4th plus 10x cubed plus 14x squared plus 250x minus 275. So then I graph it. And it looks like it crosses the x-axis at 1. It's actually a really high up graph. I could even try zoom fit, but then I might lose a little bit. I won't be able to see as well. So it looks like it crosses. Oh, that kind of messed everything up. So what I'm going to say is it crosses at 1 on my calculator. That's what it looks like. So it looks like, so from calculator, we use x equals 1 because that looked like an x-intercept, so I'm going to try that. So I'm going to do synthetic division this time. And synthetic division works really well when there's a 1 in front of the biggest degree. And it also works really well when you're not dealing with imaginary numbers. There's all kinds of ways you can do it, but I just want to stick to that. So when you see a 1 in front, synthetic division probably works. I don't care if you use synthetic or long division. Long division is the safer one. There's no restrictions put on it. It just works, okay? So let's do this. Let me show you how to do it. So the main key is for synthetic division, you take the coefficients of each of the terms, of each of the variables, and you don't skip any powers. So if one of the powers gets skipped, you have to put a 0 there. So in this case, we have a 1x to the 4th, we have 10x cubes, we have 14x squared, we have 250 x's, and then we have minus 275 no x's. And then over here, you put this little like box, and you put a 1 in it, you're 0. So this was our 0. If it was a 2, I would have put a 2 in there. Because it's a 1, I just say, okay, let me put a 1 here. Then you draw this little line with a little space, okay? So here's how it goes. You always bring down the first number, and that's why you want it to be 1. If it's not 1, we can do other stuff to get it to work. But I want to stick to this. And then you multiply this times this, and you put it right here. So 1 times 1 is 1. And then you add. So this is now addition. It's not subtraction like long division. So this becomes 11, okay? Now you do this times 11, and we get 11. And then you add, and we get 25. Then you do it again, this times this, and you get 25, right? And this becomes 275. Then you do this times this, and you get 275, you get 0. The significance of getting 0 at the end, remember, this is the remainder equals 0 means, and also this is your remainder term. This last one is the remainder. So the significance of getting 0 means that x equals 1 is a 0, which we already knew because we saw it cross the x-axis, but this is just reminding us of it. Now we have our depressed polynomial. So notice it was x to the 4th, but I just divided out one of the factors. So the power is going to decrease by 1. So this will become x cubed, right? 1x cubed plus 11x squared plus 25x's plus 275. Okay, so that is my new depressed polynomial, all right? And what I'm going to do is I'm going to hope that this is factorable. It doesn't always work this way, but sometimes it does, okay? If it doesn't, then you have to find another 0 and divide it on your calculator with synthetic or long division, okay? But I think this one is factorable. I'm going to factor out an x squared with factor by grouping, and this comes x plus 11. Plus I'm going to factor out a 25, and this becomes x plus 11. So then we have x plus 11 times x squared plus 25. Okay, so this is our other factors. So I now know that x plus 11 equals 0. So then x equals negative 11. And then I have x squared plus 25 equals 0. And this means that x squared equals negative 25. If I square root both sides, I get x equals plus or minus 5 imaginary numbers, 5 i's. Okay, because I square rooted a negative. So we're kind of to the point now where square rooting a negative is no longer illegal. It just becomes complex. Now, if you're asking for domain, it still doesn't count in the domain, so you would still throw it out. Normally, we don't work with things that have a domain and complex numbers in this level of math. So for us, our answers are negative 11 plus or, negative 11 plus or minus 5i and x equals 1. And what was the power? The degree was 4, so that's all 4 of them. So we found all 4 zeros, and we did our job, okay? So let me just write it. So we have zeros x equals negative 11, x equals 1, and x equals plus or minus 5i. Okay? And that is how you do synthetic division. Okay? All right, you guys, that'll be it for this video. Please try the homework. Let me know if you're stuck on any. Sometimes they get a little bit worse. We can go over those if you want, but that'll do it for this video. Thanks for watching.